Just to give you a little bit of perspective, at the onset of the NGL project, actually the first thing that we really did as part of NGL was to go collect data from this earthquake and to target sites that we thought would be especially valuable for site characterization. And so Dongyoup was very involved in that effort. And what he's going to be talking about is some of those really valuable case histories that are part of our database. Let me tell you a little bit about Dongyoup, and then we'll go ahead and get the proceedings underway. So Dongyoup Kwak received his Ph.D. From UCLA in 2014. He continued on as a postdoc with us for a couple of years working on NGL. And in addition to working on these case histories, he really took the lead on the first version of the NGL relational database, which was a massive effort, especially for somebody who's not a computer scientist, to undertake the just the generation of understanding of how to do it, and the rather large task of coding that was really a major accomplishment. He finished at UCLA in 2016. He went to Risk Management Solutions for a couple of years before becoming an assistant professor at Hanyang University, Erica, in Korea. So we're glad to have Dongyoup back with us, and look forward to your presentation.
All right. Thank you for your introduction, John. It's my honor to present this NGL webinar series. The Paulo Dr. Chimaro, he suggested hosting this webinar, and then I was thinking good chance to introduce the case histories that I collected during my period in UCLA, which was very happy period in my life, John and all the other people there. I'm still missing that. But anyway, so today's topic is the liquefaction case histories in strong motion stations in Tokyo Chiba area by the M9 Tohoku earthquake. So the purpose of this webinar, as I think, is to introduce the NGL case histories in Japan collected as a part of NGL efforts. The target event is a magnitude 9 Tohoku event. The target region, actually, the Tohoku events affected all the regions in Japan, but the target region in this webinar is Tokyo and Chiba area, so the metropolitan area, and the number of sites that we collected are the 6 strong motion sites and then 2 non-strong motion sites. So I'm going to introduce the 6 strong motion sites, what is the ground motion level, and then which the ground investigation, a site characterization was done, and then I'm going to introduce some ground failure feature of the 2 non-strong motion sites, and also the effort collecting the data and the available case history data. That means we collected what the available there is the ground investigation, like SPT data, CPT data, and shear wave velocity collected from SASW test, and the ground motion, because it's a strong motion sites, so there are ground motion data, so which is really valuable. And also, the most important thing is that we know what was the liquefaction performance over the sites. So we know the data of the liquefaction manifestation information. So I'm going to introduce about these data for total 8 sites in this webinar. So I think this is going to be useful for people who want to use this data set so they can understand which data is available and then what was the performance of the liquefaction at the time. And so I'm going to introduce some backgrounds about the NGL efforts briefly. So actually the efforts was done at 2014 and 15, earlier 2010. And then I will introduce each site for strong motion sites. There are 6 sites in this Tokyo and Chiba area. And then there are 2 non-strong motion sites, but there are very good characterization for lateral spreading sites, and also this the Myanmar world, which has various liquefaction performance within very small area. And then I'm going to conclude this webinar. All right. So the background, as you know, there is like a massive earthquake in 2011, and like a few days later, the gear team went to the Tokyo and Chiba area, also the other area. But the first team, as I know, including John and the other members, went to Tokyo and Chiba area, and then they visited like a strong motion site, and then decided that, oh, this station has some liquefaction manifestation or evidence this station doesn't have, or they visited like some site, like a lateral spreading site, or some site with the building performance. So from that information, at the early stage, like we targeted some stations. So which data will be valuable if we get like a site characterization? So that is the like a starting point of the NGL case history collection. So there are two phases for investigations. The first phase was like June to July 2014. So we went there. Actually, one of the UCLA former student, Alan, went there, and then he collected with the local like a contractor. He collected like a CPT data and SPT data for 6 strong motion sites and for 1 lateral spreading site. The second phase, the next year, August to September, so we figured out that the one region, like a Myanmar world, is pretty valuable, like a site for liquefaction study. So we went there, and then actually there are many data set, but there is a lack of lab test, like a triaxial test or index test and the consolidation test. So we picked the 3 locations and get the undisturbed samples for that site, and then perform the lab test. And also in this area, Dr. Ken went there and then collected the shear wave velocity data by performing the SASW for all locations within these 2 phases. So that's the background. And so at the first phase of ground investigation, so there are 2 test types. For CPT, we performed 10 CPT collection for 10 locations. So the location includes the ground motion, strong motion sites in Tokyo and Chiba area, and also the lateral spreading site, which is Urayasu seafront. And for CPT, actually, for some regions, there is no SPT data. So that means we don't know what is the index, the property of the soil. So we also get some samples using the CPT sampler for some depths in this CPT test. And for SPT, actually there are only 3 locations. So it's pretty limited because we didn't have like much budget. So the test locations should be very small number. Anyway, for SPT, we performed the 3 locations for SPT. But when do we perform the SPT? We also do the energy measurement. So we know what is the energy measurement for the SPT flow count. For second phase, so the lab test, like index test and consolidation test, and the triaxial test performed for 1 small region. The Myanmar world is Huaychume. So number of locations is 3. So I'm going to introduce where is the location for this lab test in this webinar. And then there are SASW tests for 11 locations, including the older sites that we collected CPT and SPT. So like a strong motion site and non-strong motion sites. It was the second phase as well. Right. So I'm going to introduce those 6 stations first, and then I'm going to move to the 2 non-strong motion sites in this webinar. So in 6 stations, so they are shown here. So 1 station is in here, like east end of the Chiba. There's the CHB 005, there's the Choshi area, and then the 3 sites in Chiba City, and then the 3 sites in Tokyo area. So actually, this is the same site, CHB 009 and Chiba G and GB. It is regarded as the same site. So this is just 1. So there are 3, including Choshi here, and then there are 3 within the Tokyo region. All right, so let me start introducing these sites, starting from the Choshi. So Choshi, the KNet code is a CHB J005, and the liquefaction observation we can collect from the damage report prepared by the Japanese government, as well as we can see the damage observation from the Koksedev paper. So Koksedev paper is like the earthquake spectral paper describing the case histories of the early of the reconnaissance. So we can see that which strong motion site was liquefied, or what was the performance of the ground against the liquefaction. So anyway, there are actually two sites within this small region. One site is a CHB 005, that's the KNet sites, and the other one is a CHBH 14, this is the Kiknet. So this is the KNet site, and then Kiknet site is here. So actually, the location that we performed SPT and CPT SSW is very close to the CHB 005, so which is like this location. So it's just 20 meters apart from the station. And if we take a look, the damage report by the Japanese government, so this red area means there is a liquefaction manifestation, as well as this red dot means there is some evidence of the liquefaction. But if we compare the location of the station, actually the station is just across the street, and then there is no liquefaction here. So that's the same with the observation in Koksedev. There is no evidence of the ground failure as CHB 005. However, if we take a look at the description of CHBH14 in Koksedev, so they say that there is some minor liquefaction observation, like a small sandballs in vicinity area. So I think there is some. So if we take a look at this map, actually this area is like a liquefied zone based on this damage report, and then the CHBH14 is here. So maybe that's why there is some like a small region of the liquefaction near this station. Anyway, so liquefied zone is here. Actually, this zone is a field area. So if we compare those two pictures, so this is the aerial image taken in 1965, and this is aerial image taken in 1969. So as you see, there is no land here, but at 1969, there is a land area. So it means the liquefied zone is like a relatively the new land, like a field area, performed in 1960s. So that's the base information about this site. Then this is the data collected, the photo. So we performed the CPT test at this small area, and this is the KNet station. It's very close from the location of the test. So for SPT, the investigation depth was 12.45 meter, and then we had the energy measurement. But for CPT, actually there is an excess tilting of the CPT rod, so we can. So our target depth was 15 meter actually, but due to the tilting, so they stopped the sounding at 6.47 meter. This is the photo of the CPT. And at 2015, so Dr. Ken went there, and then he performed the SSW test. So from the SSW test, we have the VS profile up to the 17 meter in this site. So we have the three site characterization like SPT, and CPT, and SSW is shown here. So this is the SPT profile from the data set, and this is a CPT. It's pretty short, but it's still valuable because the liquefaction is usually occurs at very shallow depths. And this is the result of the SSW test. So actually, the VS is pretty small, like 100 meters per second over like a 70 meter depth. So this is the ground motion. Since there are like a CHB 005 KNAT, and also there is a KICKNAT, CHBH14. So you can compare those two motions. So these are responsive spectra. And then this is the acceleration for EW direction for KNAT and KICKNAT. And then this is the velocity of the KNAT and KICKNAT. So as you compare those two, actually they are pretty similar. So for NS direction, the peak ground acceleration is like a 0.1 g, but for CHBH14, actually for EW direction, so PJ is a little bit smaller than the CHB005, which is KNAT. And then at the time, I also performed the Stagwell transform, and I counted the number of cycles, which is shown here. So this is the Stagwell transform, like a spectrogram, like a time versus frequency content of the ground motion. So it shows that there is no evidence of the liquefaction within the ground motion because there is still very high frequency contents after the large shaking. So there is some color here still. So from this one, I can see that there is no liquefaction in this station. And also I performed a trigonometric analysis at the time, actually, for the CPT data. So for CPT data, so this is a QC1 and CS, this is the CSR and CLR, and then this is the ratio, which is the factor of safety, and then this is I sub C value, and this is the soil layer. Actually, since we have the SPT data in the same location, from the SPT, you can see what's the fines content and what's the plastic limit, liquid limit, so plasticity index. So from there, you can decide, so this is susceptible to liquefaction or not. So based on that, we can calculate the factor of safety as well as decide the susceptibility of the liquefaction. Really, this is a non-liquefied site, but the factor of safety based on this trigonometric analysis, by the way, I used the Idris and Boulanger 2014 approach to calculate this CSR and CLR. Anyway, the factor of safety is less than 1 for this silty sand. So, but it's not that it's not very low factor of safety. It's like a 0.8 or 0.75. So anyway, so this, and then the thickness is not that thick. And then we have very high penetration resistance at this region. So maybe that's why there is no liquefaction in this site. Anyway, factor of safety is less than 1. So maybe this is a good point for the marginal line of the liquefaction criteria. Right. Now let me move to the next site, which is Tatsumi. So Tatsumi is actually liquefied site. Tatsumi, the KNET code is a TKY017. So Tatsumi, the station location is here. And then if we take a look, the liquefaction report, the damage report, actually this station is within the liquefied area. So red zone again means the liquefied area. The black line means, the blue red line also means the liquefied area, but the blue line, it means that there is no evidence of the liquefaction. So the location of the CPT, we performed the CPT test here. Actually, the location of CPT was here, which is in between of this blue line and red line. We couldn't do the CPT test just next to the station because it was not permitted to perform the ground investigation. But at the time, this is the construction site. That's why you could perform the CPT here. So actually the performance of this station and then this CPT location is not the same, but it was the best choice for the location of the test. So the liquefaction evidence by the Cox et al. Paper, there was a moderate liquefaction based on the description shown here. And I also collected some the the progress of the field in Tokyo region. So this area is here. So I can see that the field, this area is a field in 1945. Because this is the same with this black area, and then there is a like the year here. So this is also the field area, the field that 1945, 80 years ago. Right. So the data collected here is just a CPT. So we could investigate up to the 20-meter depths, and then we got the two samples with the CPT sampler. So two sample location is here. So this is a CPT the sounding, and then this is the photos of the CPT test and also the SASW test. And then this is a result of the SASW. So the ground motion, the shear wave velocity is 180 meters per second overall. And the two locations, so the first one, it was like clay sand. The fines content is pretty high, like more than 40%, and plasticity index is at 21. And the silt, for the second sample, it was a silty sand. The fines content is at 20%, but plasticity index is a non-plastic. So there is a ground motion as well. So this is the EW direction. So PGA was a 0.16 G, and this is the Tsunami Side, and then this is the spectral acceleration, and then this shows also the spectrogram by the S transform. But by looking at this spectrogram, then you can see that there is some spike, like evidence of the liquefaction in the ground motion, and then you can see that after this time, the high frequency contents of the ground motion is somewhat disappears. So it's very small change, like a small difference, but for this site, the high frequency content is like lower than the other site. So we can see that the ground motion includes some evidence of the liquefaction for this site. Right. So I performed the triggering analysis, and then since there is a SPT data, but there is no like a lab test data for each sample of the SPT. So we have the result of the lab test, like the index test from the CPT sampler. So for CPT sampler, we know what is the fines content for clay sand for this area, then silt sand is this one. So if we see the factor of safety, the factor of safety is pretty low. So factor of safety is like a 0.5 for this clay sand, and for this silty sand is also less than 0.5. So this clay sand, which is pretty thick, like more than 6 meters, but the plasticity index is pretty high. You can see that the I sub C value is like more than 2.5. So maybe this layer is liquefaction susceptible or not. I think it's kind of marginal case, but this is silty sand, like a 3 meter thickness. It has non-plastic feature, and I sub C is also very low. So, and also the factor of safety is very low. So this 3 meter the layer can be liquefied. So there is some controversial for this layer, but this layer I think it is liquefied the layer. Right. So that is the Tatsumi, and then by the way, all the data set, like a CPT data and SPT are inserted in the NGL database. So you can download the CPT or SPT data from there. For ground motion, actually, the ground motion time series is not there, but you can download it from the KNet or KickNet, the database, by the way. Then let me move on to the Chiba. Oh, sorry. I didn't use the mouse point in the sliding show, I think. So here. So the next one is a Chiba site. So Chiba true site actually. So KNet code is a CHB009. And actually there is another site operated by the party, the Port and Airport Research Institute. So the code name is Chiba G and GB. So there are G and GB because G means the station at the surface. GB means the station at the base. So it's a kind of the downward array. So based on the damage report as well as the Coxed paper, there is no evidence of ground failure in these locations. So same for CHB009 and same for Chiba G and GB. So CHB009, the station is here, and the test location, the CPT and SPT location was here. Actually, at the investigation time, we didn't have we didn't know the location of this Chiba G and GB. So we just selected this one because it was kind of the closest area to this CHB009 station. So we performed the CPT and SPT here, but we figured out that the Chiba G and GB is pretty close from this location. So that's kind of the lucky case because we can get the strong ground motion close to this site characterization site. So Chiba 009, that's the KNet site, and then Chiba G and GB, this is the Paris site. Anyway, there are no liquefaction evidence in these locations. And then we performed the CPT, the investigation depth 70 meter, SPT, the 50 meter. So the distance from Chiba G and GB is 100 meter for these two locations, and it's almost 1 kilometer apart from Chiba 009. So these are the CPT data set and the SPT data collected for this site. And this is the ground motion. So Chiba 009, the KNet, and Chiba G, this is a party, and Chiba GB. And this is the same site, but this is downward array. And the depth of the sensor is a minus 38 meter almost. So it has a lower PGA comparing to the Chiba G. So this is a surface motion, and this is a downward motion. If we compare these two, so the PGA is a little bit bigger for Chiba 009, but I don't think that there is like a big difference. But some difference for Chiba G is that it has like a more the spectral acceleration at the larger period than Chiba 009. Anyway, so this is the result of the S transform, but there is no evidence of the liquefaction. The high frequency contacts are still here, and then I don't see any spike in the ground motion. And this is a result of the triggering analysis. So since we have the SPT data as well as the CPT data, so we can decide the subsuitability for each layer. So these clay sands, actually the plasticity index is greater than 20, so it's kind of non-subsuitable. And for these sands, it's a non-plastic, so it is susceptible to liquefaction. But if you see the vector of safety, the vector of safety is way higher than the one. So it's not liquefiable due to the ground motion. So maybe that's the result why there is no like liquefaction in this area, even though this one is also like the field area. So I didn't explain that. So this is the image, like a map. Like I didn't get what was the year of this area, but anyway, this area is also the field area, as you see here. Right. So that's the for Chiba site, CHB009 site, and also the Paris site. And then let me move on to the Chinayaki site. So Chinayaki site is here. So actually, this is also the no ground failure site. So there's no like a description from Cox et al. For this site, but we selected this site because it has a down array, so 4 stations, as well as there is a like a port of the groundwater, the measurements in this site. So the instrumentation, the ground motion, as well as the water, the fluctuation are there. That's why we selected this site. So as you know, it was operated by the TMG, Tokyo Metropolitan Government Station, but these days I can check the station information from PARI. So I think at some time the maintenance is like moved from the TMG to PARI, I think. Anyway, there is no evidence of ground failure at stations are here, but by looking at the damage report, so we see that there are some like 2 points of the liquefaction, like these red points near the station. So station is here, that means the location is here. So at the location of the station, there's no liquefaction, but at some distance, like 300 meters, maybe from here to here, there is some evidence. I think it should be small evidence of the liquefaction. All right, so this is a zoomed view. So these, the 4 houses, that's the strong motion, the array down array stations. And then we collected the CPT close to this station. And as I said, there are down array 4 sensors at each depth, and there is also the groundwater measurement. So this is the result of the groundwater measurement. And then this is the change of the groundwater level. So the earthquake occurred at the March 11th. So after March 11th, the groundwater level is lowered for this the Chinayaki Site. So the amount of the deformation of the groundwater level is like 25 centimeter for the upper layer and 38.5 centimeter for the bottom layer. So it's about like a 30 centimeter. It's lowered after after earthquake. All right, the data collection, it was like a CPT. The depth was a 22.3 meter, and then 3 samples were collected using the CPT sampler, and also the SSW was performed at 2015. So by looking the SSW, actually the VS is around 200 meters per second, and this is the CPT result. So I'm gonna explain the triggering analysis later. And then this is the ground motion at each depth, like a 2 meter depth, 60 meter depth, and 36 meter depth, and 75 meter depth. And then this is the ground motion time series for 2 meter depth and 75 meter depth. And then this is also the Stagger transform for the surface ground motion. Then I don't see any liquefaction observation. So there is no spike, and also there are pretty large, like high frequency contents for like after the peak of the ground motion as well. All right, so this is the result of the triggering analysis. Like I apply the same procedure for all the locations, and I only use the CPT result, by the way. So there are 3 samples. 1 sample was here. So silty clay sand, fines contents 7.4 meter, 7.4%, but the plasticity index is a non-plastic. And the second one is also the same layer. It's kind of the boundary between this silty sand and sandy silt. So the fines contents of 5%, but plasticity is a non-plastic. And for this silty sand, the fines contents of 15%, but plasticity index is a non-plastic. So groundwater is here. And then if we see the ISOC value from the CPT test result, so this is pretty low. So I'm sure that this silty sand is a liquefaction substitutable, but since the penetration resistance is high, the factor of safety is pretty high for this CT sand. For second layer, actually I sub C is almost 3. I think so this is not susceptible. And same for this one. So this is kind of the marginal case. I think it's a 2.5 to 3, but the factor of safety low. But remember this site was not liquefied. So maybe this is the kind of the boundary area between liquefaction and non-liquefaction. For silted sand, it's the same. So based on the lab test, it's a non-plastic, so it could be liquefied. So and also the factor of safety is low, but still it's not the liquefied. Maybe the ground ground motion level is not that great to make the liquefaction for this case, because ground motion, the PJ, as you see here, the maximum PJ, the PJ is like a 0.1 G or 0.15 G, so it's not that big. All right, so I have 2 sites left for the ground motion sites. So the next one is a Tsunami Side. Tsunami is in this area. So the liquefaction observation is there no evidence of the ground failure. Stations, so stations is here. And if we see this damage report, actually the station is right here, but I see some like a red zone. Red zone means a liquefied zone. So the distance is 200 meters apart. But anyway, at the location of the station, there is no evidence of the liquefaction based on the damage report and based on also the Cox et al. Paper. So this area is also the field area. So if I see the evolution of the field in this Tokyo region, so this region was built at 1931 to 1945. So this is the station location, and then this is the location of the CPT test, and this is the location of the SSW. All right, so this is a ground motion. So PJ was like 0.15 G approximately, and then this is our response spectra, and then this is also Stargate transform. Then we see the high frequency contents at some like a later time of the ground motion, and then there is no spike. So we can see that there is no like a liquefaction evidence from the ground motion observation. All right, so CPT was done to 20-meter depths, and then there are 3 CPT samplers, and then a CSW test performed, and the shear velocity is fairly high, higher than the other locations. So it's more than 200 meters per second. You see this one. All right, so by performing the triggering analysis, so we have 3 samples, but the factor of safety for these 2 samples actually is close to 1. And so I see that there is no liquefaction for this upper layer. So maybe this layer can be liquefied because the factor of safety is pretty low. But unfortunately, we didn't target the sample for this silted sand, so we don't know what is the plasticity. But if we see this one, the fines content is pretty high, and the ISOC value is close to 2, but the penetration resistance is high. So there's no like a big like contribution for liquefaction based on the investigation of this triggering analysis. All right, the last site is Inage. So Inage site is a KNet CHB024. So Inage site is very famous site because there is a massive liquefaction, the severe liquefaction due to the earthquake event. So there is a large sand balls around the station. So based on the Cox et al. Paper, and also based on the damage report,
So it is liquefied area. So station is here, and it's like in this location. But by the way, for NGL, we didn't target only for severe liquefaction area because it's not actually it's valuable, but the more valuable the case history is the non-liquefied site and kind of the marginal liquefied sites. So we can decide like the CRI curve based on those data. That's why we have like more data collection for marginal liquefaction or non-liquefied site. But anyway, Inage, this is the severely liquefied site, and this is also field area. If you see this geology map, so it was like a offshore before, but right now there is a land like this one. So this is the station, the KNS station, KNS sensor. And this is the KNS sensor is within this house, is described in this photo. All right, so data collection effort, because we performed CPT only for this site. So as I said, this is kind of the famous site. So actually there are many existing the site characterization data like SPT by the Japanese report. So we have the Japanese report, the SPT with the lab test result. So we don't need to do the SPT test for this one. So we just performed the CPT test, and then we get the 3 samples with the CPT sampler. So investigation depth was 17.37 meter. All right, so this is the ground motion. So acceleration, EW direction, and velocity, W direction. And then this is the response spectrum. Then this is the Stagger transform. You see the Stagger transform, then I see like a spike of the acceleration. That's the evidence of the liquefaction. And also the high frequency contents is disappeared after this point. So that's the reason of the liquefaction. So high frequency ground motion was disappeared. So we can see that there is a liquefaction in this station, just looking this ground motion feature. Then by performing the triggering analysis, actually the CSI is pretty high. So the factor of safety is almost 0.5. So, and also the thickness of this layer is pretty thick. It's more than 6 meter, like a 7-8 meter. And from the CPT sampler, we know what is the fines content here, and the plasticity index is a non-plastic. So that's the introduction of the 6 strong motion sites, and then I'm gonna move to the non-strong motion sites. So there are 2 sites. One is a Urayasu seafront site, and the other one is a Myanmar, the H-M site. So for Urayasu seafront, there is a large lateral spreading. So we like spent like many efforts collecting the site characterization here. So we did like a 4 CPT, 1 SPT, as well as did the light observation and SSW. And for Myanmar, actually, there is like a complete observation of the liquefaction evidence performed by the Chiba University folks. So we see that which location was liquefied and which location was non-liquefied. So it's pretty valuable data set. And there is like a variation of the ground performance in small area. So that's why we targeted this region to see the liquefaction performance for each the location. So let me introduce the Urayasu seafront site first. So Urayasu seafront site, there is one of the site like targeted by the GEAR effort at 2011. So it was documented in the GEAR report number, the GEAR 025. So there is like a field reconnaissance, so measured by the people, and also for some months later, there is a ride observation before the repairments. So this is the result of the radar mapping. So it is written at the Cayenne et al. Paper, also did the gear report. So the seawall is this one. So seawall was moved like this one. Then you can also see that the movement of the ground, like a lateral, the spreading from this light observation. And also, the Professor Tokimatsu from Tokyo Tech University, he provided the airborne image, like a DM, from like this the company. So this company actually like measures the ground elevation in regular time. So we have the ground elevation before the event as well as after the event in this location. So we can compare the ground settlement by comparing those two images. So this is kind of the image like converted from the DM data. So I overlapped this airborne image with the LiDAR points here. So the black point, that's the LiDAR points, and then this blue point, that's the DM point, like an airborne image point before the event, and then the red point, that's the airborne image after the event. So of course, the LiDAR point, that's also the after event. So by comparing this LiDAR point with this the red point, actually you can see that there are like black points similar to this red point. So we can like confirm that this the point by the LiDAR is pretty exact the observation with comparing like this the additional data set like an airborne image. So we can check that how much was the settlement happened in this area. So based on like that confirmation, so we can draw some like a lateral spreading the amount like the site plan. So these red points, that's the location of the NGL efforts for site characterization. And these white dots, that's the location of the existing the SPT profiles. Anyway, from the LiDAR data set, so we couldn't make the lateral spreading displacements of the seawall. So the maximum displacement was a 2.8 meter at this location, and then this the red zone area, that's the lateral spreading zone. So we could make this kind of site plan. So I think this is pretty valuable data set to like study the lateral spreading. And also we have like a fairly many the site characterization data, so we can use it. So there are 4 CPTs, like a CPT 1 to 4. So CPT 1, the investigation depth is a 50 meter almost, and each CPT we have the one sample using the CPT sampler, and then there is one SPT. So there are 4 CPTs, so one location, that's the southwest edge of the lateral spreading, which is here. So lateral spread zone is from here to here. So CPT1 is here, and then the CPT2, that's just outside of the lateral spreading zone. So this line, that's kind of the boundary line where lateral spreading happens, and in this area, lateral spreading was not happened. So CPT2 is here. So CPT3 just inside of the lateral spreading zone, and CPT4, that's the other edge of the lateral spreading zone. So this is the plan view. So this red mark, that's the SCPT and SPT from NGL project. And then there are many SPT from the Chiba prefecture, which is this the yellow triangle. So for seismograph, actually there are like 2 seismographs near here, like HND, AKM from KU gas network, but it's pretty like a limited data set, so we couldn't get the ground acceleration from these 2 stations, unfortunately. And by performing the triggering analysis, actually comparing the triggering analysis between the 2 and 3, that's gonna be interesting. So if we compare the 2 and 3, so 3 is the CPT within the lateral spreading zone. CPT2 is the outside of the lateral spreading zone. So by comparing those two, actually the bottom part is similar to here, but the silty sand zone, and also here, this is silty sand, the CPT2 has higher resistance than CPT3, so a little bit higher. If you see this QC1CS, this one, and the QC1CS in CPT3, then you can see that the CPT2 has a higher the resistance than this one. Maybe that could be the reason why the CPT2 location, so like a no lateral spreading, is due to this higher resistance of the ground. Right. Anyway, so we could draw the cross section. So for this area, I draw the cross section for this A to A prime, which is this one. So that's the cross section of A prime, because we have the LiDAR image. Actually, the LiDAR performed within this seawall. So I could map this the elevation using the LiDAR. And unfortunately, in this area, like after the seawall, there is no LiDAR image. So this is kind of the inferred the line. And then before the events, so I just assumed that the seawall should be like a flat. There is no reason to have like a curved the ground, and then seawall is here. So this is the before the event. So you can see that what is the displacement of seawall and what is the settlement by the lateral spreading. So that was the inferred information. And then this is CH and CLML and also M. So this is from the site characterization effort. So we have the CPT and SPT with the same location. And this is a CPT2 just outside of the lateral spreading area. And 5328, this is SPT from the old like existing the literature. But unfortunately, there is a repair report of this seawall front. So there is a massive lateral spreading. So the government, the Japanese government should repair there. So they documented about the repair history. So from there, I found this kind of web. Then I figured out that the seawall has some like a small pile over here. And then there is a movement. So blue one, that's the original one. And then the red one, that's the displacement one. And then at the end of the seawall, like this area, I was thinking there's just a river wall, but I found that there's also the pile here, and then the ground was like an increase at this end area. So from this report, and also there's this information within the reports. So this is a plan for repair. So they installed like a multiple like sand columns to increase the liquefaction performance in this area. Anyway, based on the information of this report, I can like upgrade the cross section of this area. So this is after the repairment. So you see that there is a new seawall here, but there is some like a displacement between the old seawall and the new seawall. And then there is some like a difference of the elevation in new area and old area. So based on those repair report, I could upgrade the cross section. Now we have what is the pile dimension for this seawall and for this coil wall. So there is a like a pile up to like very deep depths, and I found that this P wall didn't move. Only the ground was like increased, like it becomes like water. So that's why it overturned this coil. So based on those repair report, so we have kind of the complete cross section showing the before the event and also the after the event, the elevation. And also we know what is the amount of the displacement of the seawall, which is 2 meter laterally and 0.8 meter of the settlement. All right, so that's the introduction for Ural's seafront. And then this is the last part, the Myanmar world. So there is a complete observation of the liquefaction manifestation. So this is kind of the hand drawing map performed by the Chiba University folks. So after the event, after the Tohoku event, there is a massive liquefaction within the Myanmar world area. That's just one region in the Chiba. So they walked down all the crosses, all the roads, and then they marked the heavy sand boiling, minor sand boiling, and then no liquefaction like this one. So from that damage observation, so this is just one location. So if we take the snapshot here, so that's this one, then there is a kind of a massive liquefaction area here and also here, but there is no liquefaction in this area. So it's pretty close, like 100 meters apart, but there is no liquefaction in this area and massive liquefaction. So the Chiba University performed like a various CPT tests along this line, like a C1 to C6. Actually, there is also the other CPT along this line as well. So, but they only perform the CPT, so there is no like a lab test or index test. So we targeted this area and then performed the lab test by getting the undisturbed sample. So by the way, so this is the location of the SPT and CPT from the Chiba Prefecture, Chiba City, Chiba University, and also UCLA, and also PWRI. So the city are Japanese government. So there are like 81 SPT tests and 9 CPT, and then each SPT data has a lab test as well, and then CPT also has 3 lab tests. So if we, and then there is a like observation of the liquefaction within this area. So there are pretty large data set, but we didn't include in NGL database also yet because there's too many for this area. Anyway, I want to introduce, there is some like a valuable data set here because we know the liquefaction observation as well. So let me come back to the Myanmar World Isube HOMA area. So there is a transition zone, the liquefaction area in the non-liquefied sites. So this is the boring locations. The green dot is the CPT locations. And the sand pipe shows how this area was filled using this soil discharging pipe. So this is a data collection effort. So there are like 6 CPTs, but we targeted like a highly liquefied area. So we get some undisturbed sample here. And the CPT3, that's the kind of marginal area of the liquefaction. We got the undisturbed sample here and also undisturbed sample here. So the CPT6, there is no liquefaction evidence. And we performed the lab test, like index test, consolidation test, and the triaxial test, like a CU test for using these 3 the undisturbed samples. So we have the result of the index test, and then this is the result of the gradation curve, and then this shows the consolidation test result. So looking the gradation curve, the CPT6, this is the clay layer. So the consolidation test fairly shows the consolidation feature, but for CPT1 and CPT3, actually the CPT1, this is sand, so we don't see like the distinct consolidation curve here. but the TX2, which is the marginal area, so it's kind of evolving to like a clay consolidation curve from TX1 to TX3. So it's kind of the in between the TX1 and TX3. All right, so let me conclude. Sorry, it's been like 1 hour. I didn't expect it like last like this long. But anyway, there is our NGL efforts collecting case histories in Tokyo and Chiba area. There are 6 strong motion sites, 1 with the severe liquefaction, 1 with the moderate liquefaction, and 4 with the low liquefaction evidence. And there are also 2 non-strong motion sites, 1 for lateral spreading and 1 for various liquefaction manifestation within small area. As I know, all the information are in the NGL database right now, so you can check. And then maybe it's not reviewed yet, so maybe you cannot access it. So it's gonna be opened after review. I'm not sure about the sharing the data set, but anyway, this is the valuable case histories. So I hope this webinar is useful when you want to use this case history later for liquefaction analysis. Right. Thank you for listening. So this is the end.
Thank you so much for this presentation. As you said, we're at the end of our time, but I would invite anybody who listened today that has any questions. You're welcome to submit them to Dongyoup directly, or you can always follow up at the NGL email address, which you can find on our website at nextgenerationliquefaction.org. Any last comments from Jonathan Stewart or John Smaticos?
Well, first of all, I want to thank you, Dongyoup, for preparing these materials and making it very clear what we have and how these case histories would be useful. I do just want to take a moment to thank our Japanese collaborators who worked very closely with us in identifying the sites and giving us access, or helping us get access. So Koji Tokimatsu, who Dongyoup mentioned, was kind of our main point of contact there and was extremely helpful. Akio Abe with Tokyo Soils Research, that was the firm that we engaged to do the site characterization work. And then at Chiba University, professors Nakai and Sakaguchi were of great help in identifying the sites and providing the information, the CPT data that Dongyoup mentioned.
Sorry, was that John Smaticos? Did you say something?
Yeah, I was just going to jump in and let's give my thanks to Dongyoup. Really interesting stuff, and I really appreciate you taking the time to share this with us.
Oh,
so
it's
great. Great to see you again. Yeah.
Yeah, great to see you.
All right. Thank you, everyone. So I'll send off those who are in the morning to the rest of your wonderful day, and those who are at the end of their day, have a wonderful evening.